Hello friends in person, hello friends online. A little bit different of a setup today. Chris was not able to join us in person, so um he's going to be presenting virtually, and that is a-okay. We still get our monthly community gathering in person, which is a whole lot of fun for us here at the Lagoon House. And it is so good as always to see some new faces and some familiar faces as well. So for those of you who do not know me, my name is Brooke Blosser, the Science Communications and Outreach Coordinator here at the Marine Resources Council. I kind of host these monthly Lagoon at Noons, and so if you got an email from me sometime in the last 24 hours, if you got an email from MRC, probably came from me. I do want to apologize for the last minute change of having the speaker be online instead of in person, but thank you guys still for showing up and being here for your community today. I do have a couple of things that I would like to run through with you all about Marine Resources Council programming before we get started with our speaker today. So first and foremost, tomorrow, I'm very excited. We have our first Lagoon Explorers program. It is going to be a educational program for youth grades 1 through 6. And it's going to be a science inquiry based program. If you have school-aged children, grandchildren, friends that you think would be really excited to come to the Lagoon House, please come see me after this. I'll send you the link. As of right now, we have 9 students registered, but I'm always happy to take more students for that. The next thing I'm going to clue y'all in on is we have our usual list of volunteer activities coming up this month, including First Friday Litter Sweep this Friday. That's with me. We have our Palm Bay Mangrove Workshop on June 12th. And then very exciting, we have our very first Ted Moorhead Lagoon House guided tour by yours truly, and that will be on June 13th. So the tour is free. We just request that you make a donation at the end based on how well you think the tour went, kind of vibe. And so if you would like to join that tour, or if you can't make it this time, just let me know. I have dates for guided tours all the way through the end of the month. And so really excited to show some people around and some of the projects that we have going on campus. And then the last thing that I'm going to mention, and I'm going to mention this specifically because Chris is here, is the first time that I met Chris was at my very first week on the job at Marine Resources Council last year during our 2025 Low Impact Development Conference. And it was a pretty hectic week for me because it was my first week on the job. But it was really great to hear all of the speakers about, and Chris was one of the speakers at the Low Impact Development Conference. And I'm really excited that y'all are going to have the opportunity to hear from him as well. So with that being said, we are accepting abstracts for Low Impact Development Conference 2026 with the theme being rooted in community. So if you have been working on a low impact development project in your community, including anything from stormwater pond management, rain barrels, rain gardens, and any number of other things, we invite you to submit an abstract to share that community project with our broader audience that will be attending the conference. So if you have any questions about that, I'm happy to share more information. And of course, our executive director, Dr. Lori Wilson, is leading the steering committee for that conference, and she's going to have the answers to all of your questions. So as a reminder for folks online, please drop any questions that you have into the Q&A. For folks that are in person, please go ahead and write your questions down on the notepad or the card that I passed out in front of you. I'll be taking our questions and kind of making sure that there's a dialogue going at the end of the presentation. So without further ado, I would like to present Dr. Chris Fields Johnson. He is based out of Virginia, and he has a PhD in, is it forestry and soil sciences?
Yeah, crop and soil environmental sciences, and then before
Yes.
that, I did undergraduate in forestry. Yeah.
Yes, and so we're very excited to have him here today to talk about biochar and the work that he does with Davey Institute. So although he's not here with us in Florida, hopefully we will see him again for the LID conference, question mark.
Yeah, hopefully I'll look at the dates and see if I can make it down again.
All right, so if you would like to go ahead and share your screen and get started, you can do that now.
All right. Everything look good on your end?
Yeah, all good?
All good? Okay, great. We'll go and get started. Uh, yeah, so our topic today will be biochar, which is a pretty exciting subject because of all the different things going on with both the biochar production side and biochar utilization side for all kinds of environmental management applications. Most of my experience comes from using biochar in the green industry, for landscaping and dealing with trees and turf and stuff like that. But I've also done a lot of other side experiments on using it for water quality enhancement, mine land reclamation, other interesting applications. So I'm going to go through some of the basic science behind biochar today, talk about some of the studies that I've done and some of the big studies we have going on at Davie looking in the future. And I'll also show you some of the common ways that we utilize it for land management practices. All right, so there's really kind of three sides of my research program around biochar. One, when I put biochar into the ground or into container media, I want to make sure that the plants are at least maintaining health if they're already healthy, or that their performance and health should improve. That has to be in place. We can't be damaging plant material or having it struggle because we're putting it down for other reasons. So that's kind of the foundation. And you'll see that in a lot of cases, the types of biochar that I usually recommend using are pretty universally going to be good for plants, right? Plants are going to be able to survive with pretty heavy applications. And that goes into the next two questions, which is more an area of active research. So one is how much carbon can we store in the soil? And then how can biochar play a part in that? I think you'll be able to tell by the end of this presentation that that's really a big number. It's probably unlimited because of the amounts that we can potentially use. Next question, how much water pollution can the soil remove? And I think you'll also see by the end of this presentation that biochar can play a big part in that and can remove a variety of pollutants, including nutrients that cause eutrophication and those kinds of environmental issues. So those are the three sides of it. We want to make sure plants are healthy or improving in health when we put it down. And then we're going to use it for storing atmospheric carbon and improving water quality, and then figure out how much of that we can really accomplish with char. All right, so I see biochar as being part of this life cycle where when we harvest biomass, we can upcycle a portion of it into biochar. It's a process called pyrolysis. You essentially heat up the biomass under low oxygen conditions, and it leaves a significant amount of char residue behind. While you do that, you can generate electricity, heat, bio oils, wood vinegar, which has all kinds of industrial or environmental applications. So lots of co-products you can get while you make the char. The char can then be used for filter media or remediation media, surface area for biofilms, that kind of thing, and bodies of water to clean out pollutants and reduce algae blooms, things like that. That material can then be recycled terrestrially, put onto the ground and used to increase productivity and the maintenance of plants on land. Um, we can also just take the char. It doesn't have to go through the water filtration step or anything like that. It can just be used directly onto the ground. And then hopefully it's going to increase net primary productivity. So we get a more lush green landscape that produces even more biomass and sucks even more carbon out of the atmosphere and gives us all the other benefits that lush vegetation will give us. So that in the future, there's even more biomass to harvest when those plants die or need to be trimmed back. And so we inevitably would have this kind of upcycling feedback loop, right? Where every time you take a lap around this cycle, we've sequestered more carbon, cleaned up more water, improved the health of the terrestrial landscape. And so this can be a good pathway for a sustainable future. This is why I'm interested in biochar. I realized these things in college back in 2005, and I really pursued it since then as a major focus of my research, undergraduate, graduate school, and then now at the Davie Institute as well. So if you want to look into the origins of biochar, you would find that a lot of it goes back to terra preta research. The terra preta soils, that's Portuguese for dark earth, they are in the Amazon basin in South America. So we usually think of those soils as being fairly acid and infertile. So when you cut down the rainforest vegetation and try to farm it, the ecosystem tends to fall apart pretty quickly because a lot of the nutrient and carbon content is actually bound up in that biomass that you've removed. Um, Indigenous peoples were able to take biomass, turn a large proportion of it into charcoal, mix that with other household wastes, composts, potsherds, etc., and make these really fertile dark earth soils, the terra pretas, where charcoal is really the keystone ingredient that holds it all together. It dramatically increases the amount of stable organic carbon or organic matter in the soil, and then you get all the follow-on benefits from that, from a chemical perspective, structural perspective, and especially a biological perspective, improving the performance and profile of soil microbes, which do a lot to increase fertility and ward off pathogens and help to sequester even more carbon. Um, we know this is anthropogenic. It's always associated with indigenous settlements and villages and things like that. I think it's highly likely that it was intentional, that they would have figured out pretty quickly how beneficial this was for their own forest gardening practices, and it would have become an intentional practice over time. But I don't want you to think that the Amazon is the only place that dark earths occur. So there's other examples that have been researched. Here's a few references for you. So in Japan and China, in traditional Asian agricultural practices, they would carbonize things like rice hulls, make biochar out of rice hulls. They would mix that with household waste to refertilize the fields. And there's also dark earth occurrences in central Germany. They've also been found in the Congo region in Africa. Um, but also in the United States and Canada, a really good example of this would be our charcoal enriched prairie soils. So a lot of those prairie ecosystems were burned regularly, and not just from naturally occurring fire, but a lot of it was anthropogenic fires. Again, indigenous peoples lighting the prairie on fire, usually in the late summer into fall or early winter. Every time you do that, it produces a certain amount of charcoal from that burning up uh, grass and forb biomass, right? A portion of that will turn into charcoal every time you do it. So if you do it every year and that charcoal is stable, it's going to accumulate. And scientists have actually gone in and studied prairie soils and realized that a big component of their organic matter and fertility is all this charcoal that's built up over hundreds, thousands of years of repeated prairie fire. So you can find examples of this all over the world. Really, what we're doing with biochar is trying to reverse engineer or re-engineer what was an indigenous practice and bring it into the modern world in a way that's safe and effective and can scale up and solve a lot of our environmental problems while making the land more productive or maintaining its productivity. If you're not familiar with biochar itself, I'll give you a quick little intro to some of the science behind it. Most people have the experience of sitting around a campfire, or maybe you have a wood stove or a fireplace. If you've watched that fire late into the evening, you've probably noticed that there's two distinct phases of combustion. So in the first, there's bright flame burning. So that's all the volatile component of the wood, the fuel, that's being heated up. It's vaporizing. It ignites in the air when it's exposed to oxygen and heat, and that creates the flame. But at some point, all the flame is exhausted. All that volatile matter is exhausted, and you just have burning embers or coals. If you were to extinguish the fire at that point by dousing it with water, or maybe if it's in a wood stove, you kind of damp it down, cut off the oxygen supply. Once that cools off, you'll be left with charcoal. Right? If you let it continue to burn in the presence of oxygen, it would eventually just burn down to wood ashes. So that's a key distinction to make. Is that we're not talking about wood ash here, we're talking about charcoal, which at some point you have to restrict the oxygen supply getting to the fire to end up with a high charcoal yield. So charcoal is pretty easy to make in a primitive way, right? You can start a bonfire or a debris fire. You let that burn down until 90% plus of the flame is out and it's just burning embers and coals. And then if you douse that with water, you'll have a giant pile of charcoal. And if that is made of just clean, woody biomass and debris, it's probably usable for a broad range of applications, such as what I'm going to show you a little bit later in this presentation. It will be soaking wet at first, so you can dry it out. So this is not how they would typically make charcoal for the old like iron and steel industry. For that, they would use like charcoal mounds, which is another a fairly simple way to make charcoal. For this, you'd get a fire going under an earth mound, or you could get a fire going, put a bunch of wood chips or something like that on top of it. Once it's kind of smoldering really well, then cover it with earth after the fact. I've done it that way as well. You even make a pit, get a fire going in a pit, and then cover it with earth after it's going real well. Let that burn for a number of days, usually 4 days or more, to get a really good charcoal yield. And then you would let it cool off, rake out all the earth, and you end up with a giant pile of charcoal for that. I actually used to do this with a summer camp that I ran in Virginia a number of years ago. It's really easy to make charcoal this way as well. So kind of kinetically and thermodynamically, from a chemistry perspective, charcoal is a really favorable final product of wood combustion under pretty broad conditions. Really, you just need to cut off oxygen in just the right way, uh, and you end up with a pretty high yield. The issue in modern times is that this is a pretty dirty process. One, the yield isn't necessarily great. It does create a lot of emissions, greenhouse gases and kind of noxious organic gases and things because of the incomplete combustion going on. Also, you don't have really great control over the temperature that the feedstock reaches and things like that, which do impact properties later on. So what modern pyrolysis facilities allow us to do is to very carefully control the combustion conditions, oxygen, heat, how long the biomass is exposed to the heat, and then we can have really tight controls on the emissions as well, so that hopefully the only thing getting back to the atmosphere will be mostly just water vapor and CO2, not a bunch of like particulate and noxious smoke and stuff like that. So that's what modern ways allow us to do. But all these primitive ways are still available. It's pretty easy to make charcoal and you turn it into biochar in your backyard. So here's what some the more modern facilities look like. You do have options with these. You can use round wood as a feedstock and ship it out a certain way, or you can use wood chips, green wood chips, wet wood chips, right out of the back of like an arborist truck. You've got some choices to make. Are you going to have continuous feed systems like you have up top? Are you going to have more of a batch system like you have at the bottom? There's advantages and disadvantages to each. You have other choices to make about, are you going to try to capture energy off of the system and use it to heat something, make electricity? Are you going to kind of distill out bio oils and use those for something else? Or are you just going to focus on producing biochar? Another option that's out there is having a mobile biochar processing unit. This is the Char Boss. This was kind of a collaboration between Airburner and the U.S. Forest Service. So with this, you can do cleanup after hurricanes or other storms, ice damage storms, or do like wildfire fuels mitigation treatments where you go in and thin out the forest and get out extra material that would fuel wildfire. You can then turn that material into biochar remotely. They have these smaller scale Charboss units that are something a pickup truck could pull. They have them now also the size of like a tractor trailer. You need a big truck to pull that around for doing larger scale debris cleanup and fuels projects. So there are lots of options now. Seem to be more every year for how you can make biochar with more of a modern system. All right, so let's differentiate biochar, charcoal, and black carbon. So when we talk about charcoal, we're usually talking about the material we use for cooking and heating. We also use it in metallurgy as coke for producing things like steel and silicon. A good charcoal is going to be resonant, refractory, burn flamelessly. There's pretty good field indications of when you have a high quality charcoal. We don't call it biochar until we use it to enhance the soil. So you can take like a lump charcoal that's made from wood and you could grind it up, use it as a soil amendment, then we would call it biochar as soon as you take that step. Um, there's another term out there you've probably heard called black carbon. Usually, we use that term when we find charcoal-like or biochar-like residue in the environment from forest fires, industrial soot, and other sources. These materials can persist for millions of years in ocean and lake sediments. Uh, really fine particulate black carbon can circulate in the upper atmosphere for many years. And that's really an emerging area of study in the global carbon cycle. But really, we're talking about fundamentally the same materials. It's all made up of a backbone, a carbon matrix. Um, we just use different terms sometimes when we're talking about different aspects or different places we find it or use it. All right, so this is my only real slide on organic chemistry. So I apologize if this gives anybody flashbacks to Orgo. But the fundamental structure we're looking for with biochar is that kind of graphene image at the bottom center, where you have those 6 carbon rings that form extensive chains and sheets. They're all bonded together with those sp2 hybridized carbon-carbon bonds, where the electrons can kind of bounce around with resonance between one carbon and the next. And that gives this material some really interesting properties. One, it can conduct electricity, which means it can be catalytic, can really facilitate electron transfer reactions. So for managing pollution and nutrients, things like that in soil, it's got big advantages there. Can also make nutrients accessible to plants in difficult soils. Another feature is that it really strongly resists compaction. So those graphene sheets do not like to stick to one another. You can actually use them as a lubricant, like a dry lubricant, because they kind of want to slide past each other. If you get them to stick together under intense heat and pressure, you would actually make diamonds, because diamonds are, of course, a three-dimensional matrix of carbon. Another really interesting feature is that these graphene-like structures really resist decomposition, like microbes, soil fungi, bacteria. They don't have enzymes that can really break into that structure. So it's very difficult and energetically expensive for them to break up a graphene-like structure and use it as a carbon and an energy source. So what this means is that biochar will persist in soil or in water more or less permanently. We're talking hundreds, thousands, maybe millions of years for the really complex, stable structures. That means we have a really reliable way to sequester carbon now. We can let plants pull CO2 from the atmosphere. They're going to make woody and herbaceous biomass. We then just convert that biomass into charcoal and use it as biochar or put it into the water. That essentially takes carbon out of the atmosphere and puts it into a very long-term geologic cycle where it's not going to cause global warming through the greenhouse effect. So we have a really big weapon in the fight against climate change in biochar. It has some other interesting properties like fairly high ion exchange capacity. It's comparable to what you'd find in humus and other forms of organic matter. It also has a really high surface area. If you look at the image at the bottom right, that's an electron micrograph of a loblolly pine sawdust biochar that I took in graduate school. The little tick there is a 0.5 millimeter. So you can see that all the pores, the vessels, the tracheids inside that pine wood are still intact after you make biochar. So all that internal surface area is available for nutrient exchange, water holding, microbial habitat. And you have an extremely high surface area. So 400 square meters per gram. That might be hard to visualize. But if you had like a bag, like a cubic foot sized bag, imagine like typical like bag of mulch or compost or whatever at the garden center, full of this type of biochar, it would have an internal surface area equivalent to about 60 acres. So 60 acres, right? That's the size of like 60 football fields or soccer fields, if you want to visualize that. So it's just a tremendous internal surface area for all those benefits that we can get. There are published biochar standards. So I'll refer you to the International Biochar Initiative. There's also the American Biochar Institute, another group that publishes standards. So you're going to look for things like the organic carbon content, hydrogen to carbon ratios that indicate its stability. You're going to look at levels of any contaminants. We want to see that those are very low in chars that we're going to put out into the environment. And then we can also do things like germination tests And then some other tests I do as a potting media later that you'll see when I screen chars that we're going to use at Davy. So I'll refer you to like the IBI and the American Biochar Institute as good sources for biochar standards to kind of match up which chars you might want to use for your applications and to know whether they're safe. When you get char from a supplier, you want to ask for like a third party test result and kind of match it up to published standards or specs for your projects and just make sure you've got a good match, something that's not going to create a problem. But I will say that if you have like good, clean, woody biomass material and it's pyrolyzed at kind of moderate temperatures, something like you know 350 Celsius up to maybe 650 Celsius, somewhere in that kind of Goldilocks zone. Usually it's going to turn out to be perfectly usable. It does come in different sizes and they can be used for different applications. We'll talk about that a little bit more. The chip and rice size biochar chunks are really good for maximizing porosity. So if you're trying to increase drainage and get a lot of throughput for water filtration, those are advantageous. The rice and sand size particles really mix with soil really well. If you're trying to just improve the structure and permeability and aeration in soil, the dust size stuff, which is would range from like a fine sand to a silt size particle. We would usually only use that for liquid suspensions, so you can suspend that in water with good agitation as long as your pump system can handle it and it's not going to gum things up. And you can inject that into the soil under pressure or just kind of surface drench. And you can combine it with fertilizer or other like biostimulants and whatnot. You could put it into hydroseed mixtures. That's another interesting application I haven't personally played with yet, but I think that could work really well. Usually with hydroseed mixtures, you have some kind of cellulose fiber in there. You could add this like biochar dust into that and probably get some good results as well. All right, lots of numbers on the screen here, but this just gives you a little breakdown of some of the characteristics of the different sizes of biochar. The main thing I want you to get out of this is that the bulk density of the char, it goes up as the biochar particles get smaller. The infiltration rate, your KSAT, is going to go down as biochar particles get smaller. So you could use that to kind of fine tune drainage rates for different bioretention applications, et cetera. Total porosity goes down. Microporosity will go up with smaller particles. So you get more water holding at field capacity. But macroporosity does go down with those smaller particles. So mainly just want to make you aware that a lot of these properties are dependent on the size class of biochar that you're using. So that's another thing to match up is just understand how you want the soil to function, how you want it to either store or transmit water, and then make sure the biochar that you're adding plus the other ingredients in your mix are all working together to get you to your objectives. All right, so this is a good time to talk about dust management for char. This is the main hazard for health, is that you really don't want to breathe in dry biochar dust. Most of you have probably heard of like black lung disease. There are, in most chars, low levels of polycyclic aromatic hydrocarbons, which is the same stuff you find in coal dust that causes black lung disease. So we have two methods that we're going to use to make sure nobody ever gets black lung disease from biochar. So one of my colleagues here is going to kind of show you what happens if you put down dry biochar. It's pretty dusty, right? She does a good job of staying out of the cloud of dust there. But yeah, that's not something you're going to want to be working in and around on a daily basis for long periods because there would be a risk to your respiratory health. So there's a very simple solution. We just wet the biochar down before we handle it and use it. Some chars will actually ship out wet because they actually use water to extinguish the char. Other chars with like more batch-based systems will sometimes ship out dry, which really saves on shipping weight. The dry ones are the ones you'd have to wet down before you use them for an application. If it's already coming to you wet, you don't necessarily have to wet it down again. But you want to put enough water on it to kill the dust if it comes to you dusty. Next, wear a dust mask or a respirator. If you have to handle the material, particularly before you have the opportunity to wet it down, just wear a dust mask or a respirator, like a P100 type cartridge that'll filter out all that particulate just to protect your airway. That's important. But once it's in the ground and a part of the soil, it really presents no hazard as long as you're kind of meeting all the little standards with heavy metals and things, as long as it's like a clean material. This is really the one point where you do have to be careful. All right, so one of the main things we're trying to accomplish by putting biochar in soil is to improve the structure of the soil. So the two soils on the right actually came from the soil on the left. So the one in the middle, I just tilled that up, put a lot of traffic on it for a number of years. I ended up with this really platy compacted structure. The one on the right was also a pretty highly trafficked area, but I added a lot of biochar and compost at the time of tillage. The biochar doesn't decompose. It's going to hold a lot of porosity. So it'll maintain that spongy to granular soil structure that's so beneficial for water infiltration, plant growth, getting air to circulate deeper in the soil so roots can grow deeper, and all that. So that's really the number one thing we're looking for, in addition to perhaps sequestering atmospheric carbon, as we're trying to boost organic matter and boost soil structure permanently by putting char in there. And hopefully the soil will then have a lot of resilience against future compaction. If you have a lot of foot traffic, sports fields, any vehicle traffic from lawnmowers or trucks and things driving over the soil, it should give the soil some rebound and resilience against future compaction as well. I've done a number of studies with char over the years. This is one of the earliest ones I did as a graduate student. I wanted to see if biochar could improve mine soil in the Appalachian coal field. So I just took crushed rock that was overburdened from coal mine and added different rates of biochar to it. But I also threw in a curveball treatment. I wanted to just see if the plants would grow in the pure char. I wasn't sure if it would kill the plants or I didn't really know what would happen. Just wanted to throw that treatment in there to see if there was any kind of maximum level that you could put in. Well, that would be the maximum level, wouldn't it? It would be growing plants in pure char. So it turns out that at least for shoot biomass growth, any level of char that I added to the mine soil pretty dramatically improved the growth of these black locust and American sycamore trees. But the number one treatment was actually 100% char. So this is when I first learned that, hey, biochar could be a major component of a growth media or the soil, up to and including it being a sole growth media. On the below ground biomass side, kind of a similar result, but here it was only the 100% biochar treatment that actually was statistically significantly producing more root biomass than the other treatments. You can kind of see that big loofah-looking mass of roots grown in pure biochar with a black locust tree compared to the pure spoil. Yeah, so roots seem to really respond to biochar as well as that shoot biomass. Another study I did after that one, this is a number of years ago now, I compacted a clay loam soil and was growing Atlantic white cedar, which is another important swamp species on the East Coast. Compacted it with a like steel tamping rod as hard as I could. I let these trees grow in that soil for a year, and then I went back and I measured the penetration resistance, the penetrometer. So the trees that were treated with biochar and biosolids in fairly high amounts, they had really low levels of soil compaction even after a year. The straight clay loam soil was still at 350 psi, which is root limiting. And that played out kind of how you would expect. This is above ground biomass, so it got a big boost in the growth of the trees as a result of putting the char and the biochar and biosolids combo in with the soil. And again, these soils in the right two images, they were compacted just as much as the soil on the left, but the biochar was in there to maintain porosity despite the compaction, right? So they really responded with above ground and below ground biomass. Here, the biochar, again, even without the biosolids, was the leader at producing the greatest below ground biomass root growth. So again, roots really seem to respond to biochar being incorporated in the soil. So I think there's something to this that we can really use it to get resilience against compaction and to maintain water infiltration and plant performance in areas that get a lot of high traffic. Another study I did more recently was trying to kind of figure out, okay, what level of biochar application do you really start to see good results? In the last study, I just kind of arbitrarily said, okay, let's just mix it 50-50 with the soil and see what happens. With this study, I wanted to look at several different levels and kind of see where we start to pick up some significant effects. So this was just Virginia red clay. I pounded all the structure out of it. Um, Kind of created a worst case scenario where if you have worst case compacted structureless clay, um, how much char you need to add to that without any other form of organic matter to start to see good results. So here's what that looked like. I'll just turn your attention to that 30% level. That's where I started to get significantly faster KSAT, so drainage infiltration rates, and significantly lower soil strength as measured again with a penetrometer. So that 225 psi, that's getting pretty close to a decent level. Usually in the field, we'll tell practitioners that once you start seeing levels above 200, um, that's a good action threshold to actually do something to remediate soil compaction. So 225 isn't too bad. And then it kind of dropped down to 175, 172 at the 40 and 50% level. But you see, it was significantly lower than the 20, 10, 5, and 0% levels. So that was really the cutoff. At 30% by volume, that biochar incorporated with really compacted structureless clay started to make a big impact. And that makes sense to me. I think around the 30% level, that's where you start to get significant connectivity between biochar particles, where water can really kind of find channels and flow through. And then it really starts to break up the soil strength as well. That would allow roots to grow, allow the soil to drain, allow oxygen to penetrate the soil so the roots can then survive there. All right, so another little side example. That's my daughter there a few years ago, photobombing my image of a bald cypress tree. So I planted this bald cypress as an 18-inch bare root seedling, probably 2 years old. It's kind of cut out of a field in the nursery, like a 2-year-old bare root seedling. The following year, just a little over a year later, it was 6 feet tall. A few years after that, 12 feet. Last time I went out there, it was 15 feet tall. I need to go back out there and take another picture because it's probably way bigger yet. But the way I planted this was interesting. It was kind of another trial of saying, hey, is it possible to put too much biochar in the soil around a tree when you're planting? I think the answer to that was no, because here I just dug a hole equivalent to about the size of a 5-gallon bucket. I filled the hole with pure biochar. I stuck the bald cypress seedling, uh, bare roots directly into the char and backfilled it with pure char. All I did was water it. I gave it some like slow release nitrogen fertilizer for the first couple of years, and it took off like that. I've done this with other tree species as well, so it wasn't like a one-off success. And I'm not saying that we should be necessarily putting pure char in the backfill around every tree we're planting. I'm just saying that here it caused no harm and the tree took off and grew like crazy. And I think there's something to that in the way that it's allowing um, really trouble-free root growth. Again, because the char really promotes root growth. It allows you to water around the base of the tree and get really good infiltration and penetration. And then because it drains well, you also get really good oxygenation, high oxygen content in the soil as well, which really promotes root growth and survival. So there's something to this. We can certainly use it for site prep for planting. Here's some red maples and eastern red cedar, also grown in pure char. You can pull them out. You could leave the char on the roots, kind of plant it like you would like another containerized planting. You can also wash the char off fairly easily and plant the trees as bare root seedlings. So I've had good success doing that. Growing out trees in a char-based media, pulling them out and either washing the roots off or not, and then outplanting them and getting them to perform fairly well in the field. Here's a couple more examples. On the left, that's Atlantic white cedar again. On the right, that's longleaf pine, another important species of interest to the southeast. We've got Atlantic white cedar growing in pure char. Then it's growing in 25% char, 75% peat, and then the same pattern for longleaf pine. So I think for growing like plugs and tubulings and other container grown plants, you could use char as a fairly significant portion of those. Here, you could either replace all the media with char, or you could kind of replace the perlite and vermiculite type components where you add those to something like peat to provide more porosity and drainage. because you've probably experienced this. If you just try to use pure peat as a growth media, it's pretty heavy and soaks up a lot of water, doesn't breathe very well, doesn't drain very well. So we usually add something to it to lighten it up, get more drainage through it. You could use the char for that, or you could use the char as a pure growth media. I think in this study, the plants that were in the combo treatment did a little better than the ones in the pure char, but I think either one could be viable. Here's coast redwood and giant sequoia grown in 100% biochar media in containers. Um, One advantage here is that the biochar is very lightweight. It's only a fraction of the bulk density of mineral soil. So for engineered structures, rooftops, train platforms, what have you, you could grow plants successfully and have a lot less total weight because the soil media is really light. It would be even lighter weight than using something like Stay-Lite or other things that are on the market. But we do have some studies underway looking at actual green roof media. You could blend it in with Stay-Lite or other things that are typically used, or pine bark fines, and find like an optimal rate. So we're still kind of working on what that might look like. But you could probably use it as a pure growth media for rooftops as well. So I think that there's lots of potential options there to explore. I've done some work using it as a direct filtration media. I did this at Wetland Studies and Solutions almost a decade ago now. It was one of the first studies I did at Davie. I just filled up columns with char, 36 inches tall, 12-inch diameter columns. I had an alternative treatment where I mixed about 20% biochar with 80% limestone gravel, kind of a simulation of like the Cornell University structural soil, but using biochar instead of like a clay loam soil as the fill in between the uh, chunks of gravel. And then I just spiked water with fertilizer, nitrogen, phosphorus, potassium fertilizer, and kind of measured the inputs and outputs. So on the nitrogen side, with almost 42 ppm influent, no detectable nitrogen was coming out of the bottom of the biochar column. Like the lab couldn't find it. It was below the detection limit. For the structural soil variant, about two-thirds of the nitrogen was retained. On the phosphorus side, that flipped a little bit. So I had about 90+% retention of nitrogen or phosphorus with the pure biochar, and approaching 100% nitrogen or phosphorus retention with the structural soil variant. And I think there, the limestone will react with the phosphorus, create like calcium phosphate precipitate and that kind of thing. So yeah, depending on which nutrient you're most interested in removing, you might use pure char, you might blend it with limestone or like the heat treated oyster shells or something else that'll pull more phosphorus out. There's lots of options there. This worked really well, by forcing the water column down through the filter. So I think there's ways you could integrate that into all kinds of water treatment systems, bioretention media, et cetera. Uh, After that, a little more recently, this is just a few years ago now, we played with could we take the biochar, put it into silt socks, and put it out into bodies of water and just have it kind of passively sorb and filter out pollutants, and hopefully all that surface area would get occupied by biofilms and you'd have some biological activity helping to clean out the water. So we set up a repeated randomized trial just using stock tanks. Again, we spiked these with some fertilizer to get a nice cyanobacteria algal bloom there. So some of these pictures of the control tanks will look like Mountain Dew here in a second. But this is what happened. Kind of our season averages, kind of through late summer, early fall, when we had have a little bubbler in there, some aeration to provide at least a minimum level of dissolved oxygen. The biochar sock plus broadleaf cattail growing in the biochar sock, and then it was all kind of floated near the surface of the water with some like flotation balls. We just used like the shade balls, like the black ones. You're probably familiar with those. Um, that had the clearest water, just as measured with a Secchi tube, right? So 456 millimeters Secchi measurement. The aeration plus biochar was second place, and then on down the line. Uh, on the last measurement of the seasons, this is kind of late, well, early September, the date's on there. So for this one, it was the aeration and biochar without the cattails that had the clearest water. You can kind of see what's going on there. So the no treatment, it looks like straight Mountain Dew. If you just had the biochar plus the cattails without a minimum level of dissolved oxygen from the bubbler, that didn't do too great either. That wasn't a healthy system. Still kind of looks like Mountain Dew, pretty bad visibility, water clarity. The aeration plus biochar, that was the clearest water, reading a 588 there on average. The aeration plus biochar plus cattails was a close second. But you see the water isn't really the Mountain Dew green. It had more kind of tannins and other things in it that were obstructing the water clarity. So I don't think that that one was particularly problematic at the end of the season. I just think that there was more exudates and things coming off of the cattail roots, and you're getting more tannins and things in the water. So there's something to this. So the questions will be, how do you scale it? How do you dose it for different bodies of water, and all that? That's being worked out. It is being commercially used by us and other companies that do lake management, et cetera. Exploring this, it seems to consistently work and provide benefits. But I think there will be questions moving forward about, what are the best doses? How much char do you need for a given body of water, given its level of pollution? How long does the char stay in there until you need to pull it out and replace it? And obviously, the aeration really boosted the cattail biomass growth. So they do, if those roots are kind of hanging there in the water, they do need some oxygen to do well and to produce biomass. The idea here is that you could then go back and harvest the green biomass in late summer and use that for phytoremediation, where you're just taking nutrients and whatever other pollutants the plants are taking up offsite and disposing of it or using it somewhere where it's not going to cause harm. Um, After that, I kind of moved on, looking at biochar's bioretention media. Here's cattail, woolgrass, green bulrush, all surviving in pure biochar for over a season, overwintering, all sprouting back. Didn't really lose any plants. So I think we've shown that it can be a good filter media. Now we've shown that it can be a good plant growth media. So I think the sky is the limit. I think you could really create a black hole here for nutrients, for sequestering carbon, and for dealing with excess water by incorporating biochar into bioretention media. Then the question just becomes, what do you blend it with and at what rate and whatnot for various specific applications. But here, I think you could use the pure char as a bioretention media, and I believe it would perform quite well. So you have lots of different options there. It's also fairly lightweight. When the biochar is saturated with water, the bulk density of the whole container is very, very, very slightly heavier than water itself. It's very close. So it's almost buoyant. So it's very easy to get it to float for like floating island type concepts. I know there's different companies and consultants out there doing various floating island applications for phytoremediation. I call it hydroponic phytoremediation. So yeah, you could use biochar's media for that because it's so easy to get it to float at the surface, and it's going to have all these other um, filtration and sorption of pollution type properties as well. So I've tried that again with cattail, woolgrass, green bulrush. All the plants survived for over a year. They overwintered. They all sprouted back. So I'm not really don't have many concerns yet about its viability on the growth media side. So I think that's a good option to explore. Another one that we're doing at Davy is actually taking the biochar and putting it into the Quick Reef product. So that also has things like marl, which has nutrient sorption properties. We're also looking into putting heat-treated oyster shells into the matrix, which also has really strong phosphorus sorption properties. So we do have a study that's ongoing with the Florida Institute of Technology and the University of Florida Sea Grant with a FDEP Innovative Technologies grant. That's an open study that's ongoing, looking at how adding these other ingredients to these types of artificial reef products improves the immediate nutrient sorption and other pollutant sorption, how it will affect recruitment of oysters and other aquatic life, and how it kind of shifts things long term. So we're excited about that. That's an ongoing study. Hopefully we can report back about that before too long. On land, we use it in several different ways around trees. So these are kind of our four core practices for use around trees. One, we'll top dress it, usually blend it with compost at 5 to 10% by volume, with the compost product, and put down about a quarter inch of it at a time. Down in Florida in the southeast, you could do that like twice per year because of the more subtropical climate. More temperate parts of the US, we do that like once per year in the fall. Usually we'll do it around the same time that we're top dressing or overseeding turf. We can also do hydraulic fracturing. So with the dust products, they can be mixed in with water and perhaps other liquid products and then injected into the soil under pressure. It fractures the soil. Those organic materials hold open macropores and preserve soil aggregates to improve soil structure over time. We can do vertical mulching. I've got a quick video to show you of that. You make vertical holes, usually 2 to 3 feet deep. They only need to be a couple inches wide. We'll backfill that with pure rice to chip-sized biochar. It's like a little tiny French drains kind of perforating the treatment area. Ideally, they're going to break through some kind of pan layer. Maybe it's a plow pan or construction compaction layer or something else down to a layer that'll drain better. So you'll get better site drainage. Infiltration of water will improve. Air will then penetrate the soil more deeply as it drains better, and you get deeper rooting. So you'd have more resilient plants. And then finally, air tillage, where we use an air spade or an air knife, just a jet of hypersonic or supersonic air that will break up the soil without damaging the roots. We'll blend in a pretty heavy dose of a blend of compost and char. So usually it's 1 part char, 2 parts compost. Put a couple inches of that down and then blend that into the soil to about 12 inches below the original grade. And that will take your typical kind of urban, compacted, low organic matter soil, and in a matter of a few hours, turn it into a really high functioning forest type soil where it's very high in organic matter, really good infiltration, really good structure. So those are like the four practices we would use around existing trees. This is what the air spading looks like when we're blending compost and char. So you'd go through and till first, and then put your materials down, and then use the spade to blend it in. And so this process, it doesn't harm the fibrous and woody roots. So you can do this around existing trees. Another practice is vertical mulching. So you use that air spade or air knife to make vertical holes in the soil. And then you can just flip that cone over and use it as a funnel to get your char into the holes. And now you've got a vertically mulched site. We really like char for this application because it's not going to decompose. It's going to have really maximum porosity. It's an organic product. It'll really promote rooting and microbial life. So we really like using char for vertical mulching as opposed to compost or pea stone gravel or something else, all of which would have some issues. All right, so we've seen good results with this over the years. This is just a red maple tree 2 years apart on September 1st. It was showing really high signs of establishment stress by doing this air tillage and biochar application around the tree. 2 years later, it was in perfect health, right? It was even healing over some of the old scars from sun scalding and whatnot. We can use char and turf renovations as well. If you're doing work with turf, do your core aerification and overseeding, and then put down a blend of biochar and compost, 5 to 10% by volume into a good compost. Put down a quarter inch or so of that material at a time. Should get much better germination, and it'll improve site conditions, both for the turf and trees, anything else growing there. Should really improve your surface infiltration, water use efficiency, things like that as well. And just have more resilient turf that doesn't need as much irrigation and fertilizer. Another practice we can do for site prep, and this is something you cannot do this around existing trees because it'll destroy their root systems and you'll lose them. You have to do it before you plant. With this, you put down, again, a pretty substantial layer of the 1 to 2 biochar compost blend and use a backhoe to do scoop and dump to blend that into 2 feet below original grade. We'll then typically do another lift with a couple more inches of that biochar compost blend and till that in to at least 6 inches deep to reproduce a topsoil layer. So this allows us to completely rebuild a soil profile that'll infiltrate water and filter it and grow plants on a site that was previously highly compacted, low organic matter, kind of your typical urban development site, which I know you have a lot of those in Florida. And then we can plant trees into that and expect them to do much better. So just a quick example of the scoop and dump, right? So you put down the material on the surface, then you take your backhoe, you're gonna bust up that subsoil, and then drop that blended material right down in. It's fine if it's chunky. The char and the compost will kind of fill the spaces between the chunks and allow water, air movement, and root growth. And then we take a little bit more material. Once you've got it all scooped and dumped, put a little bit more material on the surface, and then you would rototill that in, right, to reproduce topsoil. And then that avoids having to purchase topsoil and haul it in and spread that around. So this is being done in cities like Richmond, Virginia. For instance, you can go to urban heat island areas where there was not allowance made for tree planting. You can cut up concrete and asphalt. You can do soil profile rebuilding below. Make sure you mark utilities before you do this. Ask me how I know. But you can get really good results with urban reforestation using these techniques. Again, most of you have probably seen a penetrometer before. This is the same site you saw previously. The top center image is the before, right after the trees were planted. I can take my penetrometer and go right up that strip of trees, and I can bury it to the handle without ever going over 100 psi. Like, where can you ever do that in like little planting strips and parking lot islands? So you have a lot of resilience against compaction when it's done this way. You can expect trees to do a lot better because they have a lot better rooting depth. Just a little transect I ran across a treatment area, just showing that even after a year, that low compaction level really persists. We can blend biochar and compost with the existing site soil for tree planting. At Davie, we use a sliding scale where we'll use more of that blend for sites that start with less organic matter. But if you already have more than 5% organic matter, you probably don't really need to add anything unless you're really just trying to break up compaction. Then you might put a little char in there to break up the soil structure. So we do have a sliding scale we would use for tree plantings. We can be creative with how we combine treatments. So, thinking in terms of maximizing the chances for good tree establishment, that really hyper-intensive management zone right around the root ball. You really want that to be perfect. As you move out, you can do less intensive stuff that can still be effective at remediating soil and improving water infiltration and stuff, but that costs less per square foot. So like the top dressing, liquid injection, vertical mulching applications, they just cost a lot less to do per square foot. So you could do those out to the drip line or out to the full critical root zone. And then your air tillage and radial trenching, which can also be done with the air tillage, can be done kind of an intermediate zone. Right? So you can be creative with how you deploy these techniques. Another way we've done it for a post-construction or post-event site reclamation, like if you have a big festival or something, a lot of foot traffic that kind of tramples an area, you can do vertical mulching holes on a 3x3 foot grid and then do hydraulic injection kind of offset from that at the midpoints between those vertical mulch holes to try to fluff the site up and get water draining again and make it a nice viable root zone for your trees. All right, so to conclude, here's some of the key talking points that I would suggest for how we can have conversations about biochar and how it can have the best benefit in the environment. So one, improving soil structure. That's big. A nice balance of drainage and aeration and water holding capacity. It can provide all three. It will mitigate soil compaction and provide resilience against future compaction. Another big point is the storage of soil carbon. It increases the stable organic matter in the soil, like immediately. You don't have to wait for years and years and years for soil humus to build up. While it's doing that, it's sequestering atmospheric carbon. So I think this can be a really important factor in climate change mitigation. I think it is already responsible, biochar is already responsible for over 85% of durable carbon crediting globally. So it is eligible for carbon crediting and trading now. Um, Next, increasing nutrient use efficiency, having less fertilizer required to achieve the same result, and getting less runoff and leaching of fertilizer that causes water pollution and eutrophication. So we can use less fertilizer and we can expect more of it to stay on site where it's going to provide the benefit and not get into our water. And then finally, things around enhancing microbial activity. It has a really high surface area for microbial habitat, provides good air circulation for aerobic activity. Most of our beneficial microbes are going to be aerobic, so they need that airflow. And then finally, microbes, they're really important for nutrient release and cycling in soil and to protect roots from pathogens. A lot of pathogens that attack plant material are going to be um, stayed by having soil beneficial microbes protecting those root systems from those pathogens. When the beneficial microbes can't survive well, then that's when the pathogens tend to move in and take over and cause a lot of problems. Um, we do have some large studies going on in Ohio at our big research headquarters, the Seed Campus. So we've got a 2 acre area where we've stripped the topsoil off of half of the treatment blocks and replaced it with the compacted subsoil. And we also have other treatment blocks that are just kind of the native undisturbed soil. And then we've subdivided all those into other treatments, top dressing with and without biochar, compost with and without biochar. We can do tillage and no tillage, vert mulching and no vert mulching, and then a couple of treatments that involve liquid injection of some different like slow release fertility products. So we're really excited about this. We've got it established. The soil treatments in the fall. All the trees are planted. 1,600 trees were planted in the spring in this study. So we're really excited to track how all these treatments work in the long term and really learn what's the level of intervention that's needed to really restore urban soils. There's a lot of different questions we can ask with direct comparisons with this design study. A lot of stuff around just tree growth and health and stress monitoring, the fertility, respiration, and soil carbon stuff, and also looking at water, infiltration rates, soil water storage, and irrigation efficiency. All right, so I'm going to leave it there, and I'll stick around as long as there's questions or any discussion points. And so we want to really thank you for being here today and learning something about biochar. And I hope we can do a lot of good work with this moving forward.
Great, yay, let's give it a hand. Um, Thank you so much. So we have some questions in the box. I'm gonna take just a second to collect some questions around the room. As I'm walking
Okay.
around, if you guys have questions, please just hold them up so I can come grab them. We're gonna go ahead and get started with one of our online questions. Just so we can get the ball rolling.
Yeah.
Some folks in the chat want to know what is the mass balance of carbon from the production of carbon dioxide and carbon monoxide when making the char to carbon dioxide uptake from the enhanced plant blood?
The mass balance of carbon. So this process will be deeply carbon negative as long as the biochar isn't at some point burned in the future. So if you get it into the soil or the water, safe from future wildfires or people burning it for some other use, then it's very deeply carbon negative on the mass balance. So yes, while you're producing the biochar, you do get some production of like carbon dioxide, but a lot less than what the plants originally took out of the atmosphere when they were growing. So I think that's what you're getting at. But you can look at
Good,
certain
thank you.
biochar producers and look at the specific life cycle of each one. There will be a variability based on the type of biomass they're using, how far they have to ship it, and how exactly they're using it. There's a spectrum of how where exactly that carbon balance lands, but for the kind of things that I've been talking about, it will be deeply carbon negative.
Um, Awesome, thank you so much for that answer. I have another question here that um I personally really like as someone who loves local food and getting into gardening as well. Um, they said that they appreciated you addressing the carcinogenic aspects of PAHs.
Yep.
That's polycyclic aromatic hydrocarbons, for those of you who are unfamiliar. Is there a risk that PAHs or any other contaminants that might be included can go into your food from garden soil?
I suppose that, yeah, if it was unwashed, if there's unwashed biochar particles, attached to your food, you would be consuming that. And then it's a matter of like concentration and dose and all that. So I think the biggest risk is breathing in the dust and its effects on your lungs in the long term. Uh, I think the dose you would have to take of biochar contaminating food that you're eating would be pretty large before you would have any kind of reaction to it. I mean, people consume charcoal as like a health supplement, or if they have like bad gas and stuff, right? Um, so it's something to look at for sure. I hope more research is done on that so we understand that better. But I think if you're kind of doing your typical washing of root vegetables and things like that, I don't anticipate there would be any health problems from that. But that's an area of potential future study. I think the main risk is breathing the dust. That's my understanding. We don't want to do that. I've used it in my garden soil and stuff for years, and I don't really worry about the soil aspects because I wash the root vegetables.
Awesome. Um, we have a ton of questions online. I love this. This is so many questions, more than we normally get. Um, someone wants to know, it seems like high biochar application rates might reduce worm growth or an abundance of soil fauna. Have y'all studied any of this?
Reducing soil fauna. I know a lot of like beneficial mycorrhizae and other fungal organisms seem to have positive relationships with the char. Earthworms seem to have an affinity for it. It seems to promote earthworm health and reproduction as well. You can find papers on that. Um, the main drawback early on is that it does tend to pull nitrogen from the soil because of the kind of low initial nitrogen levels in the char itself. Kind of like when you put like raw wood chips in the soil, does kind of the same thing initially. So usually that self-corrects after a growing season or so. And that's one of the reasons we put it down with compost or like a fertilizer product in almost every case, except like the vertical mulching. So yeah, I'm not aware of negative effects on soil fauna if you're using the types of char that I've been discussing, which are wood-based. If you had something that was much heavier in like nutrient and salt content, let's say it was made from municipal biosolids or a manure product or some kind of herbaceous biomass with a lot of ash content, then yeah, there could be more potential negative effects on soil fauna if it was put down too heavily in too high amounts. Those kinds of biochars you would use more like a high carbon fertilizer in more limited amounts to try not to burn anything in the soil. But my understanding is that in general, it will promote soil fauna. If you use the right type of biochar is used correctly, it should help promote it. But usually, you notice with our practices, we're usually putting it down with compost because they're complementary. So that's a good caveat.
Right. I have a series of questions that are related to each other. So I'm going to do some question combining. Here in Florida, we have sandy soils and we have salt and brackish water conditions. Can
Mhm.
you elaborate on if there has been any experimentation with the biochar used in saltwater, brackish water conditions, and what the impact is on sandy soils?
All right, so for sandy soils, it should dramatically improve the water holding capacity and the nutrient retention capacity in sandy soils. So it should reduce the need for irrigation and fertilizer applications, and then subsequently reduce the kind of leaching of nutrients as well. For saline and brackish applications, I have not worked with that personally yet. I've worked with freshwater applications. Um, so I imagine the results would be similar, that you could use it in saltwater applications as a growth media or a filter media. I have not personally studied that or experimented on it because I'm deep in the interior of Virginia where all we have is fresh water. But there are numerous studies that have been done or that are ongoing. So I would encourage you to just review the literature and look into it. At Davy, yeah, we've got the study going with like adding the carbon to the quick reef, which will be a brackish to saline environment. So I'm very interested to see what we learn from that. But I don't have a great answer other than that. All indications would be that it should work just as well in a saltwater environment. But I just haven't studied it personally yet, so I can't give you any details.
Fantastic. We have a couple of folks in the chat who are interested in the cost of
Mhm.
potential biochar. Someone asks, how much do the portable biochar trailer cost to rent? And then someone else also asks, what is the cost of biochar compared to your typical fertilizer?
Okay, uh, good question. So the biochar cost per like a cubic yard or like on a volume basis varies a lot based on your source and like where you're getting it. So you can find chars on the market for as low as kind of the 65 to $75 per cubic yard range. I'm not going to like be promoting any particular like products or anything, but you can find them. And then all the way up to closer to 250 to $350 per cubic yard for other materials. So it's kind of all over the place. There's a lot of producers coming online. They have highly variable equipment and biomass streams coming in. Their cost structures are very different. Um, so yeah, it's a wide spectrum. You can probably find a lot of different biochar products in the 100 to $200 a cubic yard range if you look carefully. Um, so I think at the low end of that range, it can compete with things like peat and stay-lite and vermiculite and stuff like that, right? At the high end of the range, not as much. So you look at more specialized applications and different ways to justify it.
I love this question because this was my question that I also had. What plants are typically used to create biochar? And my alternative question was, are there any plants that you would not use to create biochar?
Okay, yeah, good question. So you can make biochar out of any plants. So in the studies that I showed you, it was wood-based char. So it was all from woody plants, from trees, right? Either from trees that were taken down for safety reasons or health reasons, or just trimmings from pruning. So the answer is you can make it out of any plants, really. Herbaceous material is going to tend to create chars with a higher ash content, and they're not going to have as much of that internal pore structure. Woody-based chars will have a much lower ash content and more of the internal pore structure. So you would select one based on your application. If you wanted something that's going to have some liming effects and be more of a high carbon fertilizer, you might go to a herbaceous based biochar that's made from switchgrass or corn stover or like whatever. Um, if you wanted something that's going to be more porous and have less of that liming potential, then you would reach for something based on wood. The pyrolysis process, it destroys a lot of the um, organic compounds in different plant material. So if you had something that was allelopathic, like tree of heaven, or something that was maybe like toxic, like you don't necessarily want to breathe the smoke from burning poison ivy or laurels or something like that. Um, all those compounds that are problematic are destroyed in the pyrolysis process, so they're gone. You could even take like railroad ties that are treated with creosote, which is an organic material from just kind of distilling smoke. The pyrolysis process completely destroys creosote. So you could take as long as they're not also treated with arsenic or copper or something. If it's railroad ties just treated with creosote, the pyrolysis destroys the creosote and it's just gone. It's turned back to CO2 and water vapor, right? Um, so yeah, you can use any plant material. Could potentially be made into biochar.
Fantastic. Um, we have a couple of questions related to the stormwater potential
Mhm.
of biochar and some of that filtering. Um, have there been any studies of stormwater runoff in these applications?
So in my study, I just did like a simulated stormwater runoff, right? I just was spiking the water with fertilizer directly. So yeah, it has been looked at. There are studies out there, and they're trying to upscale like use of biochar for stormwater management in the Chesapeake Bay region, my region now. And there's a lot of studies backing that up. So I think you could just go onto Google Scholar, find a scholarly based like database of papers and type in what you're interested in, biochar and stormwater management, see what pops up from scholarly sources, and you can review the literature and find papers that apply the closest to your situation and go from there. But yeah, there's been a lot of work done already and a lot of work ongoing. So expect a steady stream of more papers every year on that topic. Every indication would be that it would be beneficial, either putting it in kind of a direct line cartridges to filter out stormwater that's already kind of in the drainage system to bioretention media to rooftop applications. Um, every indication is that it should be helpful in a lot of different situations. Another interesting benefit will be for like marine applications or even freshwater is that it's not going to decompose. So it's not going to produce a bunch of methane as it's decomposing underwater. So that'll reduce another potential source of like greenhouse gases. So yeah, there's a lot there already to look at.
All right, we have a person from in person with us who has a question about the
Melaleuca.
Melaleuca plant, invasive plant that Florida is trying to eradicate and as a potential source for biochar.
Mhm.
Um, can the Davy Institute do a study on the efficacy of using that specific plant as biochar?
We potentially could. I think we were also looking at like using sargassum that was harvested from beaches as like a biochar substrate as well. So yeah, that's potential. Yeah, you could reach out and we could talk about that. It, it would likely make a char, and then you could run labs on it to see what its exact properties were. You know, ash content, volatile content, where it lands on pH, stuff like that. Because it would vary a little bit from like other plants, but more than likely it would make a usable char if it was pyrolyzed right. So yeah, you can reach out afterwards. Brooke can share my contact info. We could talk more, and I can connect you with people and see if they're interested in running a batch with it.
Okay, so I have a couple of questions related to specifically the Indian River Lagoon. Hopefully everyone is aware that the Marine Resources Council's goal is the restoration and preservation of the Indian River Lagoon, and so I think that's why these questions are coming up.
Mhm.
So we have one from in person. I'm gonna combine it with an online individual. What are your thoughts of using charged biochar as a slow release fertilizer to reduce some of the nutrient groundwater of the IRL?
Mhm.
And combined with an online answer, is it a solution, a potential solution from a cost benefit perspective? For Indian River Lagoon.
Yeah, so you could absolutely use charged char. There's a few ways to approach it. One would be you kind of charge it in situ. So instead of using fertilizer, you could just take an appropriate compost and add it to the soil with the char simultaneously. You can also pre-blend those products. That's a good way to charge char, just to pre-blend compost and biochar and have them stored and shipped together. Even better is to co-compost them. So you take the char, you add it to the ingredients for compost, and let them heat up and compost together. That's I think most recent science suggests that's the best way to charge your char. Um, there's other ways to do it with like different liquid inoculations. You could sparge onto it nutrients or microbial inoculations. Um, I favor more the compost approach, either pre-blending it, or blending it on site, or co-composting for a lot of reasons. But yeah, all indications are that could completely replace fertilizer utilization, and you could use that for turf, for growing beds around trees. You can use it in agriculture as well. Yeah, that should work. And then you just figure out how much you need to put down for your situation based on soil testing and what your goals are. And if done on a broad enough scale, yeah, it can make a huge difference.
Um, um, The next question, we're gonna answer live as well. This is a question from online. Can biochar with arsenic over 12 milligrams per kilogram, which I'm imagining is a EPA minimum limits standard,
Hmm.
be used in residential areas? Typical arsenic limits for soils is 2 milligrams per kilogram for residential areas and 12 for commercial areas.
All right, so you're talking about specific arsenic levels. So if you had a substrate of biomass that had arsenic in it, it was contaminated with arsenic, the pyrolysis process is not going to destroy the arsenic, right? It's still going to be in the char when you're done. So then it's a question of is it bound up or not? So I would not use a char on the site that was above the like the IBI recommendations for arsenic or other metal contaminants. Um, there's the potential that biochar will help to bind materials like that and keep them out of soil solution where they're more problematic. Um, but I would want to determine that experimentally. I think more work needs to be done on that. So I would stick to using materials that are uncontaminated to begin with. If you already have arsenic and heavy metals in your soil, could char and other forms of organic matter help to bind those up? Yes, absolutely. That's usually what you do on a site that has heavy metal contamination. You add organic matter and you increase the pH to above 7 so that those things are chelated onto organic matter and kind of bound up and no longer available in soil solution. And biochar could absolutely be used for that in combination with other forms of organic matter. Um, hopefully that answers the question. But some of these things, when it gets down to specifics, you would want to determine them experimentally with your specific site conditions to learn exactly what's going to happen when you do this combination of things and measure what the actual outcome is to know for sure. But there's a lot of papers out there already on um, environmental detoxification with char. You might be able to find something that's close to your application and design a study and figure out if it's going to work for exactly what you're talking about. It kind of depends on what
Um,
you're growing. It depends on what you're growing too, right? If it's stuff that's in the soil, there's more risk of consuming the metals that are on the vegetables and things, right? If it's fruits and stuff that doesn't really touch the soil, then it's a question of is it something that's going to be mobile and get up into the plant? Um, there's lots of other little questions to ask there.
And then the last question is kind of related to this as well. But does the biochar application reach its saturation quickly in terms of its ability to absorb nutrients? Or is it a gift that keeps giving where it can absorb those nutrients over time?
It really depends. So like nitrogen will denitrify, right? It'll make its way back to the atmosphere and as a N2 gas or N2O gas, preferably N2 gas. So in that respect, if the biochar is sorbing up lots of nitrogen, that has multiple pathways to exit. We don't want it to leach or run off, right? But if it just denitrifies, it turns back to nitrogen gas, that's fine. If the plants use it, that's also fine, right? Other things are more problematic. So, like phosphorus usually binds to soil particles and gets lodged somewhere. Hopefully, we're helping that to precipitate and not leach and run off. At some point, the char and the soil in general will be saturated, has more potential to absorb any more phosphorus. So then you'd have to either um, grow something that will extract the phosphorus, through phytoremediation, or you would need to do some top dressing or soil replacement or something to restore the absorption capacity, right? So that's going to be true for phosphorus and a lot of the other elements, right? They're not as mobile. You're either going to have to phytoremediate, grow something that has a high phosphorus demand and harvest it and get it off the site, or you're going to have to do some kind of soil replacement, or maybe put another layer of char down on the surface to add absorption. Um, where this will be more of an issue would be like bioretention media, where you're kind of funneling in. Um, there's more mass to treat. Yeah, at some point, you'd either have to harvest the biomass probably repeatedly on an annual basis, or replace the soil media in that basin once it's saturated. Again, it's something I would want to look at experimentally. You need to know the kind of profile of all the different things you're trying to filter out because they're going to be competing for um, bonding sites and all that in your bioretention media. So it's not like just phosphorus, it's the phosphorus and the nitrogen and the antifreeze and the motor oil and anything else you're trying to keep out of the water. All those things are kind of competing in complex ways for binding sites and stuff in your media. So you'd want to experiment some with a realistic profile of what's going to be going into your media and kind of know exactly what's going to happen. So yeah, in most systems, eventually you'd have to either harvest the biomass or replace the media for things like phosphorus that are not going to just volatilize and go back into the air. Nitrogen, you have more options. Does that make sense?
Yeah.
Cool.
Yeah. That was fantastic. Thank you so much. This was so informative. That was all the questions that we have today. Very engaged audience. We did have a ton of people attend in person as well. So let's give everyone a give a big hand.
Thank you.
Joining us, and everyone, I will follow up with a link to YouTube if you would like to join the presentation again. Otherwise, Chris, we'll hope to see you back in Florida soon. So,
Would love to come down again. Thanks, Brooke. Thanks for having me out.
yep.
Thank you.
Bye bye.
And then feel free to share my contact info if anybody reaches out.
Got it. Yep, not a problem. See ya.
See you next time. Bye.